picking up where we left off from the last picture. We've left the thyroid hormone, or the thyroid hormone has left the follicular cell from the thyroid gland. It's in the lumen. It has two choices. It can leave either as free T4 and T3, and it can float around the bloodstream as free hormone, or more often, it can bind to a protein for transport. Usually it's albumin. There are a couple other proteins it can bind to. So as I mentioned last time, we didn't really talk too much about albumin. It's one of the things I think the book kind of misses. You're going to get it in 415A, so it's okay. But the last 2 days, we've talked about albumin binding certain things or other proteins. So proteins in the blood can serve to help transport hormones, molecules, other things. It protects them. It keeps them from interacting with cells along the way so they can get to their target destination. There are a lot of different reasons you would bind to a protein, but most of it is transported via protein binding. Then, T4 and T3 enter a cell, whichever cell it happens to run into. If the T4 and T3 are bound to a protein, this must be released first prior to cell entry. So if the T4 is bound and is traveling through the bloodstream attached to albumin, before that T4 can enter the cell, it has to be decoupled. So usually there's an enzyme or a type of protein that allows the transport of the T4, but not the protein it's attached to, and albumin is a really big protein, so that alone helps. So that you don't take in the protein-bound T4. You take in free T4 and free T3 into the cell. Once in the cytosol, T4 gets converted to T3. So if you've taken in T3, you don't have to do that step. But if you've taken in T4, that's the pre-active form. The pre-active form becomes the active form. So then T3, which is the active form, enters the nucleus and binds to a thyroid hormone receptor, a TR. The TR, the thyroid hormone receptor, can bind to a thyroid hormone response element on the DNA. This binding alters mRNA transcription, in other words, production of mRNA. Altered mRNA production leads to altered gene expression, which leads to a change in the metabolic rate. So this is the second half. Why, when you go back and look at those carbohydrates, lipids, and proteins, and you're getting this change in metabolic rate and change in gene expression, this is how this works. The T3 is actually traveling to the nucleus and binding to something that then sticks to the DNA, which effectively turns the gene on. This isn't that different than what we looked at in a briefer way with, we talked about vitamin A can turn genes on and calcitriol can turn genes on. It's the same idea. I just expanded it out a little bit to be more specific. We don't need to learn, they have a big picture of how this binds and all the different little pieces, the XR and this is good. If you get this piece alone, is important enough to understand and will translate to all the other things that serve as nuclear binding elements and turn genes on. You can also turn genes off, but it turns out that the thyroid hormone mostly turns them on. Okay, now we've got one more little piece, which is how do we get rid of this? So, I'll just continue on. And this is what I mean by you're going to have to be creative with the numbering system. Because simultaneously, you can get rid of, if you have too much iodide, right, you can just excrete it. You can turn it into inactive hormone, and then you can excrete it after you've used the hormone. So, okay, so, last piece. So, T4 and T3, whether they're being used as T3 or whether they're just floating around as T4, can be converted to reverse T3 and T2, that's 2, by removal of an iodide. So if we think back to the structure, I'll show you the picture in a second, but there are 4 iodides attached to 2 different rings that are connected in a T4, and the same 2 rings have 3 iodides in a T3. So to deactivate these, you convert T4 to reverse T3, which means you've removed the opposite iodide from what would make it active. And T3 can be converted to T2 because you've removed an iodide and then it doesn't work anymore. So, inactive forms are excreted mainly by the kidney along with unused iodide, I minus. And then this thing over here says they can be further broken down first. It's a hormone, it's a protein. So you can send this back to, say, the liver, right? And break it down for its component parts and then just excrete the iodide. Because this is a pretty big protein, so you can get a little of it through, but mainly you got to break it down first. So, I didn't go into that much detail on the essay, but I just want you to know a little bit more so you know you're not just sending large proteins all the time through your renal system. So, I don't need you to know, although I'm going to tell you again right now, there's nothing on the exam that requires you to know that T4 becomes reverse T3 and T3 becomes T2. But those should make sense if you think that the way to deactivate something is to take an iodide off. And then, again, we'll send the iodide out. So let's look at the let me take a picture of this. Okay, questions on what you can't read on this part first? Anything?